All right, so today I'm going to talk about 7.2 integration by parts. Integration by parts is just another integration method. I'm going to start off by explaining where the formula comes from, and then I'm going to contrast it with U sub, and then from there I'm just going to do a bunch of examples, because really at the end of the day this is just a method for just churning out integrals that we couldn't do before. Okay, so the first thing is that integration by parts is kind of like reverse product rule. So to get the formula, we actually start with what we know, product rule. So product rule, if I take the derivative of two functions, u and v, and I don't know why u and v are the letters used, but they are universally used, it seems, for integration by parts. Just try to make your u and v look different. Okay, so if I take the derivative of u and v, u being a function of x and v being a function of x, we all know that we are going to take the derivative of the u, copy down the v. I'm actually going to write it backwards. So we're going to take the derivative of u with respect to x, so that's du over dx, plus, and then of course we're going to switch that process. So we're going to copy down the u and take the derivative of v. So dv over dx. I'm going to do my best to keep my u's looking different from my v's. But hopefully you'll know which is which by at least the context. Okay, so that's of course just product rule using fancy notation. So now what I'm going to do is I'm going to integrate both sides. So I'm going to integrate all three of these terms in terms of x. So that would be the integral of d over dx, uv dx is equal to the integral of v du over dx in terms of x, plus, and then u dv over dx in terms of x. Okay, so now what's going to happen here, of course, use the old fundamental theorem of calculus, the integral and the derivative basically undo each other, and what we're left here with is just uv. Okay. Here, if you basically want to play the game of, this cancels with this and this cancels with this, we're left with two integrals. The integral of v du, okay, so we're going to take the integral of v with respect to u, and the integral of u with respect to v, so u dv, okay? So now we have actually our integration by parts formula, because ultimately we're going to solve for this thing here. This is how we're going to express our integrals, and our formula will be uv minus the integral of v du is equal to the integral of u dv. Okay, so what we end up memorizing is our integration by parts formula, which is this right here. So the integral of u dv is equal to u v minus integral of v du. So at this moment, this probably doesn't have a lot of meaning to you, but this is the formula we're going to use, and ultimately we do need to memorize it. Any integral can be represented in this form. We could always apply this, but integration by parts, generally we want to apply this when we start with an integral we can't integrate, and by doing this in parts, we end up with an integral we can integrate. And hopefully through experience you'll figure out when that is. Okay, so this is the formula, and this is what you want to know. This is, once you see it, I think this is pretty easy to replicate. You just start with taking the derivative by parts and then integrate everything, and you can just do a little manipulation there. Okay, but this is the formula we're interested in right here. So let's do some examples. Okay, so we'll start off with these two examples, and I want to contrast these. So in general, and it's important that we realize that this is generally true but not always true, what we look for when we're applying integration by parts is sort of the reverse a product rule thing. So when we look at these things, they're both products, but the way we're going to do them is different. So this one actually looks like it might be reverse product rule, but it's not. It's reverse chain rule because, of course, we look for if I let u equal, so this is one we've been doing for a long time, if I let u equal x squared, we get a form of that derivative on the outside. So if I see an integral like this, I don't want to all of a sudden, which happens, people see it as a product, they go, oh, I'm going to use integration by parts. No, this is u sub, which is basically reversing that chain rule process. So this is still going to be chain rule, or excuse me, u sub. You do not want to try to do integration by parts here. So, you know, bring the 1/2 out front, x dx, that's going to be du, and that's e to the u, and this is relatively easy. And some of you might even be able to do this in your head, and that's fine as well. I don't really care if you can do an integral like this without doing u sub. Okay, so that is u sub, and that continues to be u sub. Now this one, we can't do a u sub, so always look for the u sub, but here, of course, if I let u equal x, I do not get a form of the derivative outside. There's nothing that's going to cancel here. So now I know that with this, I'm going to do integration by parts. So let's create some room here, and then I'll get down to doing this example. Okay, so here we go. So this is example 2. We have products. We thought about whether or not we could do a u sub. We can't, and so now we're going to do integration by parts. Basically, the way this works is you choose something to be u, and I'm going to talk about a trick that allows you to do this fairly easily. And you want to do it in a way that works. Let's be clear that I might apply this formula, and it's going to be true for whatever I choose u, but I might end up with an integral that I can't integrate, and that's the problem. Okay? So here I know that if I let u equal x, this is going to work. Now, you let u equal some part of your integral, then that means all the rest is going to be the dv. Okay? So we look at any integral as u dv. So we let one part be u, and we let the rest of it be dv in a way that we know that ultimately we're going to get an integral that we can deal with. Okay, so the u part is going to be just like u sub. I'm going to take the derivative of this. So the derivative of u, I'm going to call du. The derivative of x, of course, is 1, and then dx. Now, this, we're going to do the opposite. So here we're going from u to du. Here we're going dv to v. I probably should have chose a different one. So what do I do with the, e to the x? Instead of differentiating it, I integrate it. So I'm integrating e to the x, get e to the x. Like I said, probably a bad example to start with because it looks the same. But I'm integrating to get from here to here, not differentiating. So to get from u to du, I differentiate. To get from dv to v, I integrate. Okay, now I apply the formula. So I just take a look at this, uv, and like I said, ultimately we memorize this. Now, the uv has actually been pulled out of the integral. So this is the by parts, right? So you're integrating by parts. And that leaves us with something in the integral, which is going to be v, e to the x, and then du, which is dx. And now you'll notice that we're in business because we started with something we couldn't integrate, and now we have something that we can integrate. The x, e to the x just stays outside, don't forget that. Sometimes people make that mistake. Minus, and then the antiderivative of e to the x is e to the x, and then plus c. I don't want to make this video any longer than it needs to be, but I would maybe suggest that you pause the video and take the derivative of this, and you will see that it does, after I simplify it, it does end up giving me this, and that might give you some, because right now it probably seems a little bit like magic. Okay, so I'm just going to keep going on with some examples. Okay, so example 3, once again we have a product. Always consider whether a u sub will work. U sub, we're really looking for u being the guts of the composite, and then some form of the derivative being outside. We have nothing that resembles this. This is just a straight up product here. Okay, so I'm going to let u equal something, and I'm going to let dv equal something. Now I know we're going to let u equal ln of x. Now I'm going to show you this little trick. There's an acronym that allows you, that kind of helps out here. So the order to choose u. So when I'm looking, and by the way, this generally works. It doesn't always work, but it works like most of the time with these that we're going to get here. So order to choose U, there's a term called lipit. So if you just remember lipit, and you just go down the line. Okay, so lipit, so if I look at my integral and there's any logs of any kind, and that of course includes ln of x, that's a log of base e. Any logs at all, I'm going to let that equal u right off the bat. Okay, so I just go down the line here. So these are logs. If there's no logs, then I go to the next one. This is inverse trig. Okay, so, you know, like arctangent, arcsine, things of that nature. If there's any of those functions, then I let that equal u. The next thing is polynomial. Now this is a little deceiving because polynomial, in the last problem, I let u equal x. That fit into the polynomial. That's actually a monomial. So it kind of just makes sense to use the p here. But what we're talking about is sort of generic algebra. So kind of algebraic terms you saw in Algebra 1 or Algebra 2. So things like x squared, x squared plus 3x, x plus 4, any of that type of stuff. Sort of not trig, not exponential, not logs. Sort of standard algebra stuff, that falls into that P category. Okay, E, exponential. Okay, so exponential, e to the x, 3 to the x, et cetera, et cetera, et cetera. And finally, this is trig. Okay, but I will tell you that for the most part, we won't be using, there's some problems that I'm going to end up, well, you can see if we get to trig, then we're kind of off the board already. So lipit, so just think of lipit, and we're going to choose u. So I come over here and go, okay, so lipit, there's a log thing, I let that equal u. Okay, so now the dv thing is all the rest of the stuff. So the dv thing is the x, I'm going to call that x to the 1/2 dx. This we're going to derive just like it's a u sub, so that will be du. That'll be 1 over x dx. And now, remember, we're going to integrate this. So this one is better than the last example because you actually see that I'm integrating, not differentiating. So we're going to raise that a power. That'll be x to the 3/2, and then 2/3. Be careful here. The most common error I see with this is people do the differentiation instead of the integration. And now we apply the formula. So uv, so this will be 2/3 x to the 3/2 ln of x. I just switched them because it just looks a little better that way. Obviously multiplication is commutative, so uv is the same as vu, minus the integral of v du. So this is 2/3 x to the 3/2 and then 1 over x dx. Now this integral, we have to do a little bit of simplifying, but once I do a little simplifying, once again, we start with an integral, and that's the whole thing of integration by parts. You start with an integral that you can't integrate, and then you end up with an integral that you can integrate. So this will be 2/3 x to the 3/2 ln of x minus, and then let's just go ahead and bring that 2/3 out front, and then this will be x to the, and that will be 1/2 dx. Okay, so now I can integrate this. So this will be 2/3 x to the 3/2 ln of x minus 2/3. Raise that a power, so that will be 3/2. We need a 2/3 in front to cancel, and then plus c. Now, I don't mind if you leave your integrals like this, unless it says simplify, which it rarely is going to say simplify. But I'm going to go ahead and simplify this. So 2 times 2 is 4, 3 times 3 is 9, so we can just change this to 4/9. Very loud today. Hopefully you don't hear all the, it sounds like there's some video clips being shown in the background. Hopefully you can still hear me and you don't hear the murmur of that. So that is our antiderivative. Once again, you know, I encourage you at least with some of these to actually take the derivative and see it works. This one might be a little bit obnoxious, but I think it's good for you to see that this does actually work. Okay, I'm going to erase and then we're going to do a couple more examples. Okay, example 4 looks a little different. This is not our typical use or integration by parts thing because it's not a product. There's a type of integral that we're going to use integration by parts on where we can take the derivative of inverse tangent. We can take the derivative of that. We know that derivative, hopefully, but we can't integrate it. Okay. Other integrals like that we're going to use integration by parts is ln of x dx, and actually more generally any of the inverse trig things we would use integration by parts on, even though they are not strictly a product. So the way we do these is we let u equal the thing that we know the derivative of. So we know the derivative of that, but we don't know how to integrate it. And it's kind of clever how this ends up working out. And then the rest is our dv. So in this case, all we're left with for our dv is dx. Okay? So now we take the derivative of this. So we all know the derivative of inverse tangent or arctangent is 1 over 1 plus x squared. Okay? Dx. And then the antiderivative, that would be 1 dx would be x. Okay? So now, give myself some room because this one is going to take a little bit more work. So now we apply the formula. So this is equal to uv. So x inverse tangent x, and you can see what that does is the integration by parts, I brought that out of my integral, and I no longer have the arctangent inside. I'm left with just sort of algebraic things. And then I'm left with v du, so I'm just going to put that x in the numerator. Now, if you're looking at this, you go, oh wait, I still have to do a little work here. Realize that this is actually now just a standard u sub. So it might be after I apply integration by parts, I still need to do a u sub or some other algebraic manipulation. That's something you have to get used to. So I'm going to let u equal this thing. So now I'm going to do a u sub. So u is equal to 1 plus x squared. And I know that's going to work because if I take the derivative, I have a form of the derivative outside in the numerator here. So the du is equal to 2x dx. I want to replace the x dx, so I'm going to divide by 2. So du over 2 is equal to x dx. And now I'm ready to go. So x inverse tangent of x minus, I'm going to just go ahead and bring that 1/2 out front. X dx is replaced with the du, and I'm left with 1 over u, which we know the antiderivative of that. So this will be x inverse tangent of x minus 1/2 ln absolute value of u plus c. Now u is 1 plus x squared. Let me just make the point that that's actually never going to be negative. So I don't need the absolute value here, so I'm just going to drop that. If you leave the absolute value in here, that's not something I'm going to take off points for, but it is extraneous in this situation. Okay, so another time we use integration by parts when we can take the derivative of something, but we don't know how to integrate it. And like I said, this is how we're actually going to integrate any of the other inverse trig derivatives, and also a log, ln of x, things of that nature. Okay, all right. So I'm going to do 2 more examples, and then we'll call it a day. Okay, example 5, the integral of x squared cosine x dx. So this is back to sort of the standard setup for integration by parts, a product that we can apply u sub on. So realize that we're going to let u equal x squared. Once again, I'm just following that Lippitt an acronym. So there's no logs, there's no inverse trig, but there is the polynomial, or what I would just say is generic algebra. Okay, dv is going to be all the rest of the stuff. So dv is equal to cosine x dx. So du is equal to 2x dx. v is equal to sine x. Remember, we're integrating this, not differentiating it. Very common error is people differentiate and end up with a negative here. So just be careful with that. So this is equal to uv, so x squared sine x minus the integral of v du. So let's just bring that 2 out front, x, and then sine x dx. Okay, Now we take a look at this integral and you might realize that, oh my goodness, we have to do integration by parts again, and that's exactly right because we have a product where a u sub doesn't work. So I'm just going to apply integration by parts again. And if you're sitting here going, this is really annoying, I don't disagree. There is a trick to do these that I'll show you in the next example. Okay, so there is a trick to doing these ones where we have to apply integration by parts multiple times. So we're going to let u equal x. dv is going to be the rest of the stuff. So that's the sine x dx. The derivative of x, 1 dx. Now we're going to antiderive to get this. The antiderivative of sine is negative cosine x. And now here be careful because we have this negative 2 out front. So this will be x squared sine x minus 2. And I would suggest bracketing this off because ultimately we've got to distribute that negative 2 through this. So uv, so that's going to give me negative x cosine x minus the integral of v du. So I'm subtracting that negative, so I'm going to make this plus the integral of cosine x dx and that bracket. Okay, now we're in business. So I'm going to go ahead and distribute this. So this will give me plus 2. If you left it bracketed, I'm not going to take off for it. I actually don't mind. You could just leave it bracketed off if you wanted to, but you obviously don't need to. And the antiderivative of cosine is going to be positive sine x, right? So then I'm going to just distribute this. So this will be negative 2 and then sine of x plus c. And there you go. Okay, one more example, and in that example I'm going to show you how to do the multi-step ones quicker. Okay, last example. So this is similar to the last problem, except we have x to the third and e to the x. So let me explain what's going to happen here. If I did this sort of straight, the way we've been doing all these, I would actually have to apply integration by parts 3 times. If you notice, we had the x squared, so we had to apply the integration by parts to get that x squared down to x, and we apply it again to get rid of that x and just leave us with the sine cosine thing. Okay, this one we would have to do integration by parts to bring it down to x squared, then we have to apply it again to bring it down to x, and then we have to apply it down again just to get the e to the x thing. So that's quite cumbersome and annoying. So this method called tabular method works. It doesn't always work, so don't apply it with the ones where we can just do integration by parts once. It's specific when we have something that's polynomial in nature, something that's going to decompose down to 0. So if I keep taking derivatives of that, that's going to end up at 0. And another thing that doesn't decompose, like e to the x, and what I mean by that is I can take derivatives of e to the x all day, it's never going to be 0. Same is true for like sine x and cosine x. If I take derivatives of those things, they just sort of flip back and forth with negatives and positives. So these are the things we want to use tabular method on. And so tabular method is just an algorithm really that kind of keeps us all organized, and it makes it kind of nice for us. So what we do is we make 2 columns here, a u column and a dv column. The u column, we put what would be the u, and once again we just follow Lipit. So that's going to be x to the third. The dv column, we put the e to the x. Now we start with the u column, and what we want to do is we want to take the derivative of our u thing down to 0. So we're going to have rows for each derivative. So this will be 3x squared, 6x, 6, and then 0. And then we're going to integrate this thing to match it. Now e to the x is easy because it's e to the x. The most other common example, if you're working with sine x and cosine x, the one thing I would just be careful, remember we're integrating those, and the sine x and cosine x, you just have to be very, very careful with the negative and positive. Okay, now the last thing is, on this side, we're going to keep track of what the value is, either positive or negative. So the first thing will be positive, and the reason why this switches is because of the subtraction here. So the first term is going to end up being positive, the next term is going to be minus, plus, minus. We actually don't need the last one. And what we do is we draw straight across, straight across, straight across, straight across, and then here we go down 1, down 1, down 1, down 1. So we make this little chart, and this chart actually tells me what the integration is going to be. So once again, we use this when we have something that has usually a polynomial of a certain degree with like e to the x or sine x, cosine x. Okay, so now we just follow these rows. So positive x to the third e to the x minus 3x squared e to the x plus 6x e to the x, and then minus 6 e to the x and plus c, and that is much, much easier than applying this formula 3 different times. Okay, so that's the tabular method. All right, so that is integration by parts, and you've watched me do a bunch of examples. Now it's your turn. It's really very important with these that you get the practice in and get used to this, and also identifying when integration by parts is something that's going to work. I will tell you, when you work in this section in the book 7.2, not all the problems you're given in that section are integration by parts. So there are some U subs. Look out for that, because you don't want to go applying this long process when a U sub would have worked. Okay? So, go ahead and put the time in, practice these things, and, if you get lost along the way, I would go back and watch parts of this video.